Let's talk about the chain rule, which is a tool we're going to use to find the derivative of composite functions. And if we're going to talk about composite functions, if we're going to talk about the chain rule and composite functions, the first thing we might want to remember is what is a composite function? Recall from your discussion in advanced functions that composite functions are formed by combining one function with another. To form a composite, one function is substituted into the input of a second function. In function notation, if g of x and h of x are two functions, then the composite of g and h is the function f of x, defined by f of x equals g of h of x, or g bracket h bracket x bracket bracket, where g of x is the outer function and h of x is the inner function. It is read as g composed with h, or g of h of x. Personally, I've never used this composed nomenclature, so I'm used to saying g of h of x, so that's how we're going to say it. And let's just visualize, thinking about our function as a machine, what that's going to look like. So basically, h of x is my inner function, so with h of x, I'm going to put my x value into my function machine, which is going to be my function h, and the output is going to be h of x. And then that output becomes the input for my next function machine. So it's going to go into my outer function, g, and give me my output of g of x. So I'm putting an x value in, I'm applying some operation, some function h, and then the output of that function becomes the input for my second function g, and then I find g of x, or g of h of x, I guess I should say. G of h of x. As an example, let g of x equal x squared and h of x equal 3x plus 5. Let's find f of x equals g of h of x. So we're going to have f of x equals, h is our inner one, so g of h of x. So g is x squared. Instead of x, I'm going to write my h function, 3x plus 5 squared. And we can color code this. So my g function is going to be the green outer part. And my h function is going to be my orange inner part. So green is my skeleton of outer function. And our orange is the inner function is the input of our outer function. And we've already demonstrated that with our function machine diagrams up at the top of our page as well. Next up, let's find p of x, which is h of g of x. So we've reversed the positions here. So let's choose a different color and let's take a look. So p of x equals h of g of x. So they've switched positions, the inner and outer functions. So I'm going to have my h of x, which is 3. Instead of x, I'm going to put my g of x, which is x squared plus 5. So 3x squared plus 5 is my p of x. And we can just color code that real quick. G of x can be green. And h of x will be orange. And so those pieces are coming together to form our composite function. All right, let's take a look at a specific composite function and see what else we can describe about it. In our first example, we were given the inner and outer function. Now we're just being given the overall function, and we need to try to identify the inner and outer portions on our own. So let's consider the composite function f of x equals 3x squared minus 7x, and the whole thing is to the power of 5. can we imagine an inner function and an outer function? So remember, the outer function is like our skeleton. Actually, kind of think like the inner function being the skeleton and the outer function being like the flesh wrapped around it, but we'll follow the notation in the note here. So basically, the skeleton of our outer equation is going to be this part right here, some variable to the power of 5. Let's continue reading. If we express the inner function as u equals h of x equals 3x squared minus 7, so we're just using u to simplify and represent a more complicated function. So u is like a new variable, but really, we're not really changing anything here. We're just making our life easier by using a single letter to represent our inner function. And then the outer function can be g of u equals u to the power of 5. Now the chain rule tells us that we can find the derivative of f of x as follows. So this is our new tool. So if I have the function, so if we have f of x equals g of h of x, then our derivative is going to be, we're going to take the derivative of our outer function, g prime, h of x stays inside as the argument, times h prime x. So let's read here. We take the derivative of the outer function, which is our g of x, and then multiply by the derivative of the inner function. So in our example here, derivative of the outer function was my g prime x, and multiply by the derivative of the inner function, which was h prime x. In Leibniz notation, if y equals g of u and u equals h of x, then both are differentiable functions, then dy dx equals dy du times dy dx. And you can kind of think about that canceling out. And this equals, it's simplified to dy dx if we just treated it like a regular fraction. So you can think about that's a way that allows this to be true. So if f of x equals 3x squared minus 7x to the power of 5, let's just identify our components here once again. So f of x equals g of h of x. G of x is going to be x to the power of 5. H of x is going to be our inner function, which is 3x squared minus 7x. Then let's write that out. So this is going to equal the derivative of g of x. So the derivative of x to the power of 5 is 5x to the power of 4. But instead of x, I'm going to have my h of x. So 5x to the power of 4. But the input for this function is not x. It's my h of x function. So instead, we're going to write that in. 3x squared minus 7x. We should color code that all the way through. H of x equals 3x squared minus 7x times the derivative of h of x, which is going to be 6x minus 7. All right, that looks pretty good. Let's just tidy it up a little bit. So the derivative of our function is going to be f prime x equals 5 times 6x minus 7 times 3x squared minus 7x to the power of 4. And we're just putting our higher power at the end, but it doesn't really matter. There isn't really anything else we can do here. I think we're good. We can also write this more simply in the Leibniz notation if we have f of x equals u to the power of 5. And off to the side, we'll note that u is equal to my h of x, which is 3x squared minus 7x. And then this derivative, f prime x, is equal to 5u to the power of 4. And then if we wanted to, we could just sub this back in. I believe this part represents this part right here. And we still need to do our du dx. So we're finding the derivative of 3x squared minus 7x. So that's going to give us 2, oops, no it's not, 6x minus 7. So we have these two pieces here. And so we can multiply them together. So our derivative is equal to 5, 3x squared minus 7x to the power of 4, 6x minus 7. And the order is just different, but otherwise we found the same thing. And we're just multiplying, so the order doesn't really matter. All right, so there's our first dip of our toe into the pool of working with composite functions using chain rule. Let's continue and see what else we can do. For the following composite functions, identify the inner and outer function, and then differentiate using the chain rule. So we're going to have, I like to think of it as f of x equals g of h of x. So once again, we'll kind of color code. G can be our outer function each time, and h of x can be our inner function. So let's identify our inner function here. That's going to be what's inside the brackets. And the outer part is our g of x. So we'll identify our parts off to the side here because I find that easier. G of x is our outer portion. So that's going to be bracket x bracket negative 2. H of x is going to be 4x squared plus 3x. And let's remember what our chain rule said. Once I get this lined up properly again. All right, I'm just going to leave that there. It's not worth the hassle. Chain rule says f prime x equals g prime of h of x times the derivative of h of x. So f prime x equals g prime h of x times h prime x. All right, let's go ahead and do this. So f prime x is going to equal the derivative of g prime. So that negative 2 is going to come up here to the front. So it's just power rule once again. Negative 2 to the power of something to the power of negative 3, because we subtract 1 from our exponent. And our inner argument is just my h of x function. So that's going to remain unchanged. And then we're going to multiply by the derivative of our inner function. So the 2 multiplies by the 4 to give us 8, x to the power of 1 plus 3. And let's rewrite this with positive exponents. So we're going to get f prime x equals negative 2, 8x plus 3 over, and because we have a negative exponent here, we're going to flip it down. So we're going to use up the negative, moving that term into the denominator. So we're going to have 4x squared plus 3x to the power of 3. And we don't need to expand or anything. We can just leave it the way it is. If anything, we want to list it with as many like factors as we can, like fully factored. So we could do, can't factor anything out of the top. 8x plus 3 is already reduced as much as possible. But on the bottom, we could factor out an x cubed. So I could have I think there's a mistake in the answer key I'm looking at. We were going to factor out an x though. So we can have x bracket 4x plus 3 to the power of 3. Actually, that is going to be an x cubed. Let's see why. So I have 4x cubed plus 3x to the power of 3. If I want to factor out a 3, that's also going to be to the power of 3 still. X plus 3 power of 3. And so it's going to be x cubed is the factor that I take out. You don't need to do that. We'll call this a bonus step. As long as you can get to this point, we're good to go. All right, let's take a look at our second question. We have y equals root 2x minus 3x to the power of 5. That looks delightful. I'm going to copy my formula down for a moment so I can still view it while I work. All right, let's keep going. Let's identify the outer and inner components of our function here. So my g of x is my outer component, and g of x is going to be equal to square root of my argument, so x. H of x is my inner component, and that's going to be the 2x minus 3x to the power of 5. And we can color code green on the outside, red on the inside. All right, let's take a look and see what we can do with our chain rule here. So y prime is going to be, so the derivative of my outer function. Actually, I'm going to rewrite my y function first. You could probably follow without me writing it, but more notation is more better. 2x minus 3x to the power of 5 to the power of half. So we can also rewrite this as x to the half, and expressing everything in terms of exponents instead of having square root symbols mixed in as well helps make our life a little easier. So we know we're just working with exponents using our exponent rules, etc. So let's find our y prime. Let's find the derivative of my outer function. So half argument to the power of, I subtract 1 from my exponent, so my half becomes a negative half, and the inner term remains the same. Multiplied by the derivative of my inner term, which is going to be x minus 15x squared. Sorry, 15x to the power of 4. All right, can we tidy this up? Can we do anything? Well, I can. Actually, I made another mistake as well. Sorry. Let's just redo that part. So let's find the derivative of this part. So the derivative of 2x is going to be 2. The derivative of negative 3x to the power of 5. The 5 comes down, multiplied by the negative 3 to get negative 15. X, and I subtract 1 from the exponent, so now it's 4. All right, now let's see if we can tidy this up a little bit. Anything with a negative exponent, we're going to make positive and bring that to the bottom. So this term here has that negative exponent, so I'm going to flip it down, and we use up the negative when our numerator turns into a denominator, or a term moves from our numerator to our denominator. So let's take a look. We are going to have 2x minus 3x to the power of 5 to the power of positive half now because we used up the negative. And on the top, we're going to have 2 minus 15x to the power of 4. So I don't really need that 1 there up front anymore. We can rewrite this once again. Y prime is equal to 2 minus 15x to the power of 4 over 2 square root of 2x minus 3x to the power of 5. And then I can just cancel out these 2's. No, I can't do that. And I did that on purpose because I have students in all grades, even grade 12s, even in calculus, who think they can simplify by canceling out any term that appears on the top and bottom of a fraction, regardless of what operation is being performed. If we were multiplying, if I had 2 times negative 15 over 2 times my square root whatever, that's fine. I can't do it unless it's all being multiplied. This is being subtracted. I cannot cancel the terms like that. Do not cancel the terms like that. So we're going to leave it the way it is. And this is okay. This is pretty good. But we can simplify further by considering the fact that we want to rationalize our denominator. Sorry, we're not even going to do that, but we can do something similar to what we did in our previous question, where on the bottom we have 2x minus 3x to the power of 5 to the power of half. And we can factor out an x. But like we saw before, the exponent is still going to apply to both parts. So I could rewrite this as I've done here. Oh, sorry. Let's try this again. I'm not going to edit this video. I'm just going to leave these mistakes in so you can see that teachers make mistakes too, but also how we go back and fix them. So I'm going to rewrite this. 2x minus 3x to the power of 5 to the power of half. I can factor an x out, so I have to actually take it out of the terms I'm factoring it out of. So 2 minus 3x to the power of 4. And remember, the exponent still applies to that factor that I just pulled out. So I can rewrite it this way. So I could rewrite this as y prime equals 2 minus 15x to the power of 4 over 2 times x to the power of half, or root x and root 2 minus 3x to the power of 4. It's not necessary. It's just more of an example that we could do it that way. We can also think about this in terms of our Leibniz notation for a moment. And I just want to think if I want to do this for both examples. Yeah, we can do that. So let's represent g of u equals u to the power of half, and this is our outer function. Our inner function, u equals h of x equals 2x minus 3x to the power of 5, and that's our inner function. And if I want to find g prime u, it's going to be half u to the negative half times u prime. So it's going to be half u is 2x minus 3x to the power of 5 to the power of negative half times the derivative of u, which is 2 minus 15x to the power of 4. So we can think about it that way as well if you find that helpful. Mostly, I mean, we're still doing the same thing. It's just a matter of notation. Moving on, let's take a look at a few more examples, C and D and E. In our first question here, for C, we're told that g of x is equal to sine 2 of x. So let's label g of u. And I'm actually going to rewrite this just so we're not confusing our notation. I'm going to use f of x once again equals sine 2x. So gu, our outer function, is equal to sine of our argument, of u, where u is equal to h of x, which is my inner function, which is 2x. So I know g prime u is going to be g prime not quite. Let's take a step back. I'm not finding the derivative of g, I'm finding the derivative of f, which includes g and h. So f prime x equals g prime u times u prime, or du dx. So we've identified each component. Let's go ahead and solve. So f prime x is going to equal the derivative of sine is cosine, and our argument remains the same. That's still my inner function, times the derivative of my inner function, and the derivative of 2x is equal to 2. So f prime x is equal to 2 cosine 2x. And that really wasn't too bad. It's not that hard to find. We didn't have to do any complicated calculations or deal with a whole bunch of exponents. We just need to keep track of our rules and remember what we've talked about with the derivatives of trigonometric functions. Let's take a look at D. And some of you asked a question about this yesterday. You had something similar in the homework and we hadn't learned that yet. Anytime where one of our variables is replaced with a function, that's where we're going to use something like chain rule. That's an example of a composite function. So once again, let's identify g of u So my outer function is going to be e to the x. U is my h of x. And it's going to be 3x squared. E to the u. It's just habit that I keep using x instead. But yeah, we'll be careful with that as we work. So what do we know? Y prime is going to be g prime of u times u prime. So g prime is going to be, well, we know the derivative of e to the power of u is just going to be, so g prime u. Remember, we know about Euler's number when we're dealing with it as the base of our exponent function, that it's its own derivative, so nothing changes there. And u prime is going to be 6x. So let's plug those values in. G prime of u, so e to the u, where u is just our original argument, which is 3x squared, times the derivative of u, which is 6x. So we're going to find out that y prime is equal to 6x times Euler's number, 3 to the power of 3x squared. And be careful with this, especially if you're trying to type this. It can get confusing because we don't want to write 3 times 2. Like, don't get confused or think it's 3 times x times 2 or whatever. It's 3 times x to the power of 2. So just be careful. Make sure you're writing that clearly as you go. Finally, our last question. Y equals 5 to the power of x squared minus 3x. So our g of u, our outer function, is going to be 5 to the power of u. U is our inner function, so u is going to be equal to x squared minus 3x. The derivative, g prime u, is going to be equal to 5u ln 5. Remember, we learned that rule previously, so we're not going to explain why that works. We'll just use what we've already learned. It's already a tool we have in our toolbox. And u prime is equal to 2x minus 3. So let's do up our derivative here. Y prime is equal to, so the derivative of our outer function, which is going to be 5u times ln 5. Remember, we know what u equals, so we can plug that in right away. And that is x squared minus 3x times my u prime, which is 2x minus 3. And we can rewrite that so it looks a little more neatlier, but still not great. We're going to have ln 5. Remember, that's just a number. We're going to have 2x minus 3. And we'll put our stuff with exponents at the end. 5 to the power of x squared minus 3x. All right, that looks pretty good to me. In our next section, we're going to take a look at chain rule applications, but I'm actually going to stop here and publish that as a separate video.